This video is about Rice's theorem. We've seen a lot of properties about Turing machines, and we've seen that these properties are undecidable. For example, checking if a Turing machine holds on the empty tape, if it holds for any input. There are a lot of problems that are undecidable. And actually, this result is generalized by Rice's theorem. What it usually considers, or why it's so important, so practical, is that usually when you design software, you have some kind of specification in mind. You have some idea what the program should do. So you have the idea of a specification. This specification somehow defines the desired behavior of your system. And the behavior of a system usually is defined in terms of some kind of input-output behavior. So you have some input here, and you have some output, and you have a specification that somehow specifies how the input relates to the output. So the I/O behavior. That's what you might have specified. Of course, you can only specify some kind of input-output behavior that is computable in general. You cannot specify, I mean, you can do, but it makes no sense to specify something that's already known to be undecidable. So at least in principle, there must be one program at least that would actually yield this specified behavior. So the specification must be computable in principle. Computable in principle. So that's the usual approach. And software engineering, you have specification, you have gathered requirements, what your program should do, and of course these things are usually computable. And now the question is, you have an implementation, maybe several implementations, and you would like to check whether the implementation actually satisfies the requirement, the specification. You have several implementations. They can be different. One specification can have multiple implementations. For example, you have specified it should be sorting. You can have a quick sort, a merge sort, heap sort, whatever. So there are different possible implementations. And you would like to check whether the implementations actually satisfy the requirement. That's something you would like to know, because you have a programmer who realized your specification, would like to know whether it actually satisfies the specification. So the problem is, does an implementation satisfy the specification? For example, you can assume that for example, this one does not, but maybe this one here does. And this one here, maybe not as well. So that's actually the question, does it satisfy the specification? And it turns out, by Rice's theorem, that this is actually undecidable. So once you have some kind of specification, as long as it is it's not really trivial, then it's undecidable whether your program actually satisfies the specification. And by trivial, I mean only two trivial cases. And the two trivial cases is, first one is the program does anything. That's always true, because whatever program it is, it does anything. And the other question is, does it nothing? And as a program always does anything, even if there's only an infinite loop, it does something. It loops. So the question, does it nothing, is always false, and the question, does it anything, is always true. And apart from these two trivial cases, every specification is undecidable. And that's what Rice's theorem is all about. And the first thing is we need to formalize the specification, and Rice's theorem comes in two different versions. First version is in a function version, the second one is in a language version. For the function version, we have a specification, function version, and the specification is given by a set S, a set of Turing computable functions, and S is not the empty set, and it is not the set of all functions, all computable functions. So then it's called a non-trivial set. So it must be just a set of Turing computable functions, and then the problem is, does a given Turing machine MW compute a function in S? That's the problem we would like to decide. It's the same problem here. We have some implementation, some code. We would like to know whether it complies with the specification. That's the function version, and there's also a language version. And the language version, I will use this color. For the language version, here our specification is given in terms of sets of languages. So here our specification S is a set of Turing acceptable languages. And again, it's non-trivial, so it's not the empty set. Not empty, because the Turing machine accepts some language, even if it's the empty language. Empty meaning here just that the specification may not be empty. It may contain the empty language, however. So S is a set of Turing acceptable languages. The set not empty, and not the set of all Turing acceptable languages, not the set of all Turing acceptable languages. And then we have the problem, does a given Turing machine MW accept a language in S? And Rice's theorem states that in both cases this problem is undecidable. So this is undecidable. And this, of course, also limits our possibility that for program verification to check whether a program complies with the specification. That's why it's so complicated. Of course, for special programs, we might be able to prove that a program complies with the specification. However, in general, this theorem is only about the general case. In general, it's impossible. So it's impossible to derive an algorithm that always works. For some particular programs, it's of course possible.